Great. 14 in total.
Oh, okay.
So hey, Zoom room, how's the sound?
Can you hear us?
Thumbs up, down?
So,
Yes,
We can hear you.
Perfect, great, thank
Okay.
you.
Great. Yeah.
Welcome, Efric. Welcome, Spartans. Welcome, guests, to our Efric Nuclear Theory Seminar today. It's my pleasure to introduce the speaker, who is David Reinhardt with the German Aerospace Center DLR. That is sort of the German version of NASA. And David is a visitor here at MSU. He's a PhD student, and you are going to stay here until through tomorrow.
Yeah.
Okay, great. So he's going to talk about, by the way, his PhD advisor is Wolfgang Schleich, and he's going to talk about an algebraic geometric classification of the solutions of the 1D Gross-Pitaevskii equation. Take it away, David.
Yeah. Thank you very much for coming. I also want to say hello to the people who are watching this online. Thank you very much for attending this talk. I appreciate it. Those of you who haven't seen me in the past 2 days, I'm David Reinhardt. As Christian already introduced me, I'm with the German Aerospace Center, which is kind of new. It's like 2 or 3 years old. It was brought up in 2019, and I'm with the BCAL project, which is like the successor mission of the Carr mission, which is currently on the International Space Station. So it's like the cold atom laboratory in space. And they do kind of experiments with Bose-Einstein condensation in space, where they don't need to worry about gravity and can realize different shell geometries with Bose-Einstein condensate mixtures, or investigate some further fundamental physics, for example. And I'm part of the theory group in the BCAL project. And this Institute of Quantum Technologies also has some other projects like atomic clocks and also other stuff. So if you're interested in this, you can look up online what else we are doing. Today I'm going to talk about an algebraic geometric classification of the solutions of the 1D Gross-Pitaevskii equation. And this is kind of a structured manner to kind of see what kind of solutions you get. And we classify it by looking for the roots of a polynomial, which I will introduce to you briefly. So before I go into detail, let me briefly go over the content I will present to you in the next probably 45 minutes. First, I will show you the 1D Gross-Pitaevskii equation in the hydrodynamic framework we consider. This is kind of a modeling transform, or it is the modeling transform we use, get a kind of a different representation. And I will briefly go over this so that you can kind of understand our method we are using for classifying these solutions. And then I will show you how we can use this new form to classify the solutions. And then, okay, the solutions of the 1D Gross-Pitaevskii equation, this is like, it's a partial differential equation, nonlinear, but still it's kind of old. And of course, most solutions are known and there's nothing new to it. So we thought about it, okay, what can we do with this? And then we thought about, let's include three-body interactions, elastic three-body interactions for the first part, and see what we can deduce from our previously done work for the case of three-body interactions or three-body collisions. And then finally, I will go to talk about the conformal duality, which we discovered a very interesting thing that we can kind of relate both systems, the two-body system and the three-body interaction system, which is kind of neat and something that we didn't found in the literature yet, and we are currently investigating it further. So, as I said, the time-independent Gross-Pitaevskii equation is basically a nonlinear Schrödinger equation. I think Gross was like American and Pitaevskii is from the Soviet Union, and as far as I know, they never met. So this kind of the thing, they named it after the Bose, and they kind of thought, at least that was I was told, that they just looked for an easy extension of the linear Schrödinger equation, and they said, okay, let's add the self-modulating term and see what kind of new types of solutions or what kind of new kind of behavior we're going to observe. So this is basically it. There's this self-modulating term with the interaction strength G in front of here. And there's, of course, like some sign of energy or chemical potential giving rise to the energy states of the system. And usually the Gross-Pitaevskii equation is used in a variety of different fields of physics. For example, like you use this in for describing light waves in nonlinear optical fibers. Maybe you have heard of the nonlinear Carr effect or something like this. This can also be described by the nonlinear Gross-Pitaevskii equation. And important to note is that for a Bose-Einstein condensate, this is basically a mean field approximations of the many-body Schrödinger equation. And it kind of gives you a very nice differential equation, which kind of reduces this, condenses like the many-body Schrödinger equation to this nice form. And interesting about this is that, but we need to keep in mind that it also only describes the zero mode of the condensate. So we do not, usually you could go beyond this. There's a Bogolyubov equation, for example, who considers first order exchange process with an atomic cloud, which usually take place. But this is kind of a very basic approximation for describing a Bose-Einstein condensate, and it's only valid at t equals to 0. So the coupling constant G here is proportional usually to the S-wave scattering length, which is valid for very low energies. And for G largest to than 0, we call it a repulsive interaction or defocusing. And for G smaller than 0, we call it attractive interaction or focusing attraction. So next on, we're gonna kind of transform this equation into two different equations. Therefore, we use the Nadelung transform, which kind of splits up the real part, or like the absolute value of the wave function, and multiplies it with some phase. So it's like a polar coordinate representation, you could say. And if you do so, then you can solve the real part and the imaginary part separately. And for the real part, you end up with a differential equation for the density, which on the right-hand side, you see like a polynomial, which is cubic in the density. And of course, you have here the gradient squared. For the phase, you get another very nice differential equation, which is given by this expression in the red box. And there's also an additional constant of integration, which kind of can be associated with the particle flux, the integration constant alpha here. And of course, be aware that we kind of labeled, might be important later on, that we kind of use an order here. So B is for the two-body interaction case, the coefficient B, and the subscript M3 refers to the power of the density it stands in front of. So as you can see, these two coefficients always kind of mesh, so that we kind of have everything ordered here. So before going deeper in, as I said, this is kind of a polynomial in N. So for the graphs I'm drawing, I just call this the right-hand side of this differential equation, P of N. And here, let me briefly go into the coefficients so that you know a bit about how it comes down. Here you see in the leading coefficient of the cubic term, you just have the interaction strength G with some prefactors. For B2, you basically have the negative chemical potential. And for B1, you have an additional integration constant, which is kind of related to the energy density. And in B0, you have the minus the squared particle flux.
Hi. There is a question to you.
Yeah.
Pavel, you want to ask?
Yeah, sure.
Yeah, I have a question. Why the slides are not shared?
Sorry, very sorry for that. Thank you for pointing this out. This is kind of essential that you see what I'm talking about.
You need to share.
Okay. Yes, that's right.
Okay. So how do I do this? Bildschirm Präsentation? No, that's not the wrong one.
Zoom.
So nobody told me I had to log into Zoom.
Oh,
He said it's fine if I have it on here, and he said they will just like kind of.
Okay, so sorry then. Can you log into Zoom and then just share?
Sure. Can you log into your Zoom account, because you usually use Skype? Let me see. I need to connect. So we came like an hour early and tried to check everything, and but still should have come 2 hours early. So now maybe you want to log in.
So in the email that I sent you, there's the link. You just need to.
Okay, I need to open it.
But you have Zoom installed, right?
I don't think so, not on this computer, because this is like a blank computer just for the travel.
So your talks on PDF?
It's a PowerPoint. I can send it to anybody.
You want to just do it from this computer?
Yeah, I suggested this initially, but
And he refused.
he said it's fine and I should not worry.
Okay, sorry about that.
But I sent it to.
Okay, so let's be quick. So I think it's faster to install Zoom on your computer than.
I don't have administration rights here.
Okay, do you have a USB stick? A USB drive?
Zoom implement, and we are not allowed to install anything else on this computer, unfortunately. I think it's the easiest way. I just send it per email to someone.
Okay.
If you don't mind. In the browser, that's fine too. Thank you for the suggestion. That solves a lot of problems. So let's see. And when did you send it to me? Like, you know the date? For the Zoom link, Christian check.
Dean, I think I have host rights.
Let me just.
So if I get the slides, I can show them.
I'm gonna grab my computer. I think that's the quickest solution.
Okay.
I'll be right back.
Okay. Just a second.
It's on pastries.
No, everything's fine. So I'm just waiting for his email.
You mean for the Zoom?
Yeah, in-person theory seminar, theory Tuesday. Is this a Zoom link? Yeah, via Zoom webinar, passcode. This is the one, right?
942-7974.
Yeah, this should be working. Okay. Join from your browser. Verstanden. Bildschirm freigeben. Ist da. So let me see.
Got it, I think.
Okay.
That's, you can now see. Oh, sorry.
Yeah, we can see, but it would be good.
I should mute the microphone.
A slideshow.
Yeah. Otherwise, we just get an echo. So, great. So, but now you Einstein. Now I just need to change kind of the screens, right? Can I just pull it up? Sorry. So you might want to stay with. Can we enlarge this further?
But it's displaying there like that.
Yeah. Notice that the people online, they are like currently, I think, seeing this one. Or what are they seeing?
Yeah. Let's see what it's there.
Maybe Bildschirm presentation.
Oh, okay, yeah.
So if I go through this, no,
He's got it working here, but it's
can be like duplicated that they see the same as on the screen here.
yeah. Here, let's just
just share the full screens of the application.
yeah.
Okay, that's kind of what I suggest.
Yeah, I don't know.
Okay, let's so and now let's do the presentation again and then go back to Zoom and share the presentation screen, right? So, what is up? neue Freigabe. So, now I think that should work.
Okay.
So let me see if I can skip through and you see this too.
It's very good now.
Yeah, perfect. Still the presenter now is not responding.
But that's connected to your.
Yeah.
Okay. You might need to press the.
No, it works.
Perfect. Okay.
Oh,
Thanks.
sorry very much for this delay, and thank you for pointing this out to me. This was very unfortunate, but now everyone is seeing everything, I think. Is this right?
Yes. Yes.
Okay, great. Thank you for your patience. So I might give you a quick reminder of what I talked about on this slide. As you can see, this here is just a simple Schrödinger equation, and then you have this additional self-modulating part and mu instead of like the energy of the system, and G scales like the S-ray scattering length, and you can have G is larger than 0 or G is smaller than 0, and then we call it repulsive or attractive interaction, as I said. So there's not very much different from the basic Schrödinger equation. Now, as I said, there's the Madelung transform. This is basically the absolute value of the wave function times the exponential of its phase. And if we transform this, as I said, you get a very nice differential equation, which is cubic in the density and basically just a cubic polynomial. And you have here, you have the squared gradient. And you see, like I said, the coefficients subscript refer to the power of the density. And here you have the differential equation that we need to kind of calculate the phase. You see here this additional integration constant alpha, which comes in when we integrate it one time. And this refers to the particle flux. And of course, here we see n of x, which is the density. So now we have like two differential equations from the original problem. And what we're going to do is we're going to look at the differential equation for the density. And if we do so, let me quick give you an example of what the coefficients are about. The leading coefficients of the cubic term refers to the interaction strength. So the sign of G determines kind of the slope of this polynomial here. Then we have like the second coefficient B2, which refers to the negative chemical potential. Then we have some kind of beta here, which is an additional integration constant and is related to the energy density of the system. And then again, we have here the squared particle flux with an overall minus sign, which will become important later on. And of course, like you can easily check, this is a very nice differential equation. It's separable, so you can separate the variables and can write down the integral, and everything is fine. That's very nice. And you could solve this integral and then invert it and get the solution n of x if it's like if this integral exists. And yeah, as you might know, this integral is given in terms of elliptic functions, as the differential equation up here basically resembles an elliptical curve. If you would replace this, for example, the squared gradient with an y squared or with y, then you would have y squared, and then you could have some cubic polynomial in x, for example, and this would just give you these algebraic curves. I don't know if you're familiar with that, but that's why it's called an elliptical integral here. So let me give you a brief example of how we're going to use this. So this polynomial, this p of n here, the polynomial in the density, can be drawn. For example, here we have a positive slope, which means that g is repulsive. So kind of you see it comes from minus infinity and goes to infinity here. And I will focus on a very good example with three distinct roots. So we have for example, in our definition, a positive discriminant. And then we have three regions above the in the first quadrant, which we need to consider. Why do we need to consider the regions in the first quadrant? You might ask. Yeah, if you looked up here, here's the polynomial, the square root of the polynomial, and if there's a negative number under the square root, this would give rise to like a complex spatial coordinate, which we want to avoid, since this would not give rise to a physical solution. So we want to consider the regions which are enclosed by the roots or half open, like the region after the third square root and the third root. And the region in between is kind of the region we consider for our integration. So we might want to start with by going from n1 to some density which is smaller than n2, but larger than n1 naturally. Or we could start by with n3 as the lower bound and go to infinity, or basically n smaller than infinity, and kind of solve this integral too. So as I said, we can only consider regions in the first quadrant, and there are other constraints that we need to consider. For example, the sign of the curve of the leading coefficients is basically determined. It's kind of cut off here by the sign of the interaction strength. I already mentioned that. And another important part is the intercept with the y-axis, so to say, needs to be negative. As you might recall, the constant offset coefficients of the polynomial, it was given by -4 times alpha squared, and alpha was the particle flux, and of course this is a negative number, and so the intercept of this polynomial is for sure is at most 0. So this is something we need to consider when drawing this graph and identifying which regions we're gonna consider when performing the integration. So now let's actually solve this integral, and for a quick example, if you do so for going from n1 to some other density n, which is smaller than n2, we would get this function Sn squared with some coefficients and an additional parameter k. So for those of you who are not familiar with this kind of solution, it's basically very much like a normal trigonometric sign, but the sign, as you might recall, is defined on the unit circle, and the radius is of course a constant. If you now have an ellipse, the radius is no more a constant, but depends on the angle. And you can define something similar to a normal sign on the unit circle on the ellipse, which is kind of an elliptical sign. Then they call it, or it's the Jacobi elliptical Sn function. And this Jacobi elliptical S function is equal to the normal sine function if these parameter k, which kind of quantifies the departure from our unit circle for the ellipse, is equal to 0, then we would just have this function equal to the sine squared. And if you go this parameter k can go up to almost 1, so or can approach 1, and then you would have another limiting case, which I will talk about later on. And as you can see, basically what we have here in the argument is like we have the coefficient C3, we have some gamma, which is basically just depends on the root. We have C3, which depends on the interaction strength. And then we have like this parameter k, which kind of determines the shape of the function with an additional parameter. And then, of course, we have like here the two roots, which kind of are the prefactors on give us a small offset. So, for example, if I consider box boundaries, you know the solution from the Schrödinger case. For the 0 mode, you just have half an oscillation. For the second mode, you get a full oscillation. And this is kind of the same picture here. We need to impose that n1 is equal to 0, so that the wave function vanishes at the edges, and then n1 drops out. And here you can see I, for example, plotted two modes. The first mode looks a bit more deformed like a sine, so it's a bit more broader around the peak. And also you can see the second mode is also like oscillating like the normal full sine period, or sine squared period, but it's a bit also a bit broader around around the peak. And this is kind of how you would like proceed basically with any other region you would consider as well. So this is kind of how you would construct the solution given the picture we are considering the hydrodynamic framework. So before I go on, there are other kinds of solutions you might have heard on. There are like Soliton's kind of solutions, and you might have heard of them, but in case you have not heard of them, I will give you a quick reminder on what Solitons are. So here you basically see a wave packet, a water wave packet traveling in a tank, and as you might see, the shape of the wave packet stays the same over a long distance, and it's not dispersive. So it maintains a shape and it travels with a constant velocity. And this is kind of the defining property of the soliton. So it maintains a shape over a long distance, and it kind of needs the nonlinearity. You don't have this with the standard Schrödinger equation. The self-modulating term is important to kind of get this, since like in a normal Schrödinger equation, you would kind of have this dispersive behavior, like for example, a Gaussian wave packet would just disperse. And here you see that the nonlinearity kind of counteracts this dispersion. And when they kind of dynamically balance, you would get like this shape persistent wave packet. And also another important property is if two solitons would interact, they would go right through each other and would not kind of affect the shape of each other after they have gone through each other. So this is also an important property. So a bit of history here, like a quick slide on history. They were first scientifically reported by John Scott Russell, who observed them in a Scottish canal, and there were like horses like pulling a boat. And as you see here, there are waves like in a V-shape form from the front of the boat to the side. And if the velocity of the boat minus the flow velocity of the river and the velocity of the waves coincide, then these wave trains flap open and the soliton trains move ahead. So this is kind of the picture where we observed the soliton for the first time, and then he had kind of a water tank and had all these experiments and wanted to kind of, he was an engineer and wanted to kind of understand how these solitons form. And yeah, basically he did the first discovery of a soliton. And of course, you can have this also in Bose-Einstein condensates. And here you see, for example, the first evidence for a dark soliton. A dark soliton is basically, you have a constant background density, and then you have like a small kink in this background density, which is usually kind of darkening the background density. And here you see this compared to the numerical simulation for the setup. And the guy who did this is a professor at Durham University. And as you see, there's like this thin stripe here in the condensate. So white is basically it's a background condensate, so with a constant background density. And you see the soliton is kind of moving through the condensate and is oscillating back and forth. And so this is kind of what we also observe in Bose-Einstein condensation. So, and what about like the soliton solutions? Now you are aware of what solitons are. How do we get these solitons? And the solitons we can get if we have a double root. And the interesting thing is, if we have the double root, if the double root is the second root numerically, then we would get a dark soliton. And if it's the first root numerically, then we get a bright soliton, which is basically an elevation in a constant background density, and just like a normal wave packet, you could consider that. So as I said, it's kind of a kink in a constant background density, and it has this hyperbolic tangent form and shape for the standard Gross-Pitaevskii equation. So, and this you get just by solving the same integral, and now you can solve it with elementary functions, since the double root kind of destroys the elliptical properties of the elliptic functions. And as you might recall, the double root here for the second case needs to be at the origin, since there's no other way to draw this graph and intersecting the y-axis below or exactly at 0 than having it having it here, and also of course having like an enclosed region in the first quadrant. So these are the two constraints we need to match here to kind of have a physical relevant solution. And it has also like a very nice shape. The tails are decaying exponentially, and this has this 1 over the squared cosine hyperbolic cosine, and or sometimes they call it secants squared. And this is also a really nice localized wave packet you get as a solution. So as I said, for double roots, you can classify and say, okay, you get soliton-like solutions. Now, of course, these solutions are well known. You could, in principle, when I go back, you can here have also like this region you could also consider, and you would kind of get irregular solutions which diverge at the origin. I do not cover this here, but this might become important later on. So you might want to remember that there's this kind of region which I neglected in telling you how to classify these solutions. And now we were satisfied we could kind of explain why there are different solutions arising that do not arise in the Schrödinger case. In the Schrödinger case, for example, you cannot have nodeless solution, and by drawing these graphs, you can easily see what kind of solutions, what kind of properties they have. You can deduce from the graph what kind of solution you will get. And then, of course, we wanted to see, okay, what is, if we are going beyond, now we have this method in drawing these graphs and solving these integral, and how about I just add a polynomial and a quadratic term, and what does this correspond to? And this corresponds actually to having three-body collisions, elastic three-body collisions. Still, you need to remember, this is still in the mean field regime, but there's like a quadratic term and in the wave function, in the absolute value of the wave function that we are adding with an additional coupling constant. So as you can see, I just renamed G as G2 because now G2 refers to the two-body interaction, and G3 tilde refers to the three-body interaction, and everything else basically remains the same. So basically, we just have another leading coefficients, and the rest basically stays the same. And of course, like before, we can just like separate the variables, perform the integration, and interestingly, it's what I was not aware of initially. I thought initially, just like from thinking about it, okay, now if we go quadratic, this is be a hyperelliptical integral, but that is not the case. It's actually still an elliptical integral, and that's something you would not. I at least did not expect this. But I looked it up, and of course, it's an elliptical integral. And why this is the case will become clearer later on. And now you can kind of think about what you can do with that. So kind of you see in red indicated, you see a curve which kind of resembles the normal cubic case, where you have just a positive slope, so repulsive interaction. And now in teal coloring, over this curve, we laid in like the quadratic curve with also a positive three-body interaction constant. And now, as you can see, basically for some, if you would kind of consider kind of neglect this region here, you see you could in principle find some graph that kind of coincides with that graph, and kind of this would already hints that there might be some kind of similarity involved. But still, this is kind of just to give you an idea, and still we getting just one enclosed region between the second and the third root here for like a positive overall slope, and so if you compare these two differential equations and like in a factored form, so we consider it in the we consider it factored. Like we just here have three roots, the leading coefficients of the two-body interaction is involved here, B3. And here for the three-body interactions, I use the lettering for the coefficients with C to kind of B is the second letter in the alphabet and C is the third letter, so kind of to keep an overview about what I'm doing. And now you see like here are just three and four different distinct roots, and you have here three distinct roots. And so there's kind of the question, what does relate these two differential equations? Is there kind of a mapping? We can map these differential equations into each other, and kind of what does this tell us about the system, and what kind of consequences arise by doing that? And this is kind of the question we were facing. And if you look at, for example, at the solution we already derived, like just the box solution in the case, or basically the box solution, which is only which is also valid for periodic boundaries. For periodic boundaries, N1 is generally not zero, but for box boundaries, N1 of course needs to be zero. And if you compare it for the same region in the quadratic case, you see that it has this form, which is kind of, yeah, it kind of looks the same kind of function is appearing, just like there's like now a fraction of this function with some offset terms. And you could ask yourself, okay, just by looking at it, what kind of transformation may be involved, kind of, if I assume for simplicity that these coefficients here in front of the x, and of course the parameter k, kind of, if I just suppose they are equal to each other, and what kind of transformation do I need to perform to map this function to that function, or this density to that density? And as you might recall from your course in complex analysis, it's just a real value modulus transform you use for that. So the modulus transform is something like a times x plus some offset b over c times x plus d. And this is basically what you can do with this density. You can just use this transformation, a real value transformation, since we're considering the density here, and map this onto this solution. And of course, this is just like this is not like a really good mathematical argument, but of course you can like already get an impression what is going to happen. And if you want to do this in a very good manner, so if you want to kind of be mathematically more rigorous, you need to perform a birational transformation, and you also of course need to transform the gradient here according to this transformation. So as you can see, as I mentioned, this is just the transformation of the density with real value coefficients. The group you might notice is the projective linear group over the real numbers in 2 dimensions. And here you have the gradient, which also needs to be taken care of. So you might, when you perform this, you plug this in, and then you can choose the coefficients in such a way that you kind of send when you're going from 3-body from the fourth or from the quadratic polynomial to the 2-body to the cubic polynomial. You kind of see you can choose the coefficients in a way that one of the roots is kind of sent to infinity. So you kind of map one root to infinity, and this kind of relates these two systems. Of course, if you would go the other way, then you would kind of pull or kind of take a root from infinity to like a finite distance. And this is kind of the inverse transformation. You can, of course, invert this transformation. And this is kind of how you then go from one system to each other. And this is by like pulling these roots. Of course, you need to be careful. These roots should be not be numerically not be in the middle, because this kind of would distort the polynomial, and this makes no sense. So it should be the root at the either the smallest or the largest root, but then you can like play around with it, and then you can kind of transform these graphs into each other. So you can kind of see, if I would just pull a root from infinity here, I would just kind of like making this finite here, not going to minus infinity, and cross the 0 line, this the real axis, and kind of get kind of additional solutions. So if you go back, for example, briefly, if I could here pull a root from infinity, from plus infinity, I would get here an additional enclosed region in the first quadrant, which I would give rise to a finite solution. And so kind of the irregular solutions we have in the case of 2-body interactions can kind of be finitized or regularized by using this transformation. So basically in the 3-body case, this is a regular solution, but in the 2-body case, this is an irregular solution. And this is kind of what links these two solutions. And the solutions mostly look very much alike, even if you have, for example, here it looks, on first glance, it looks like it could be different, but if you actually considering it, the denominator is always finite, and it basically has a very similar shape. It's very comparable. You see some deviations. For the solitons, you get like 3-body interaction solitons. They also have like this tangent shape. So basically, you can also transform the soliton density or the bright soliton density, and then just put the hyperbolic tangent in here, and then you could also see that still this looks on the first glimpse a bit that this might be more complicated form, but that still has basically the same form. There are minor deviations, but that's fine. And what's also interesting, maybe before I finish my talk, I might want to tell you, I don't have the slide here, but if you would have like a triple root in the 2-body case, you could actually imagine something like this, a triple root, and you would expect, okay, normally like multiple roots could give rise to solitons, as we could see that double roots give us solitons. And as you do, you can do this, but of course this is an irregular solution, since in a 2-body case it's not bounded, so it kind of goes here and then it goes up to infinity and just crossing the real axis one time. But if you now kind of pull a root from infinity and finitizes this, this would give you rise to a kind of different kind of soliton, which not has exponential decaying tails, but now this would kind of has a Lorentz profile with a power law scaling for the tails, which is kind of neat. That's what you can have. And also one interesting solution already been found, but we could derive this again if you had like two double roots, then you get something which is like a semi-infinite meta distribution, which is basically some kind of Fermi-Dirac distribution from the functional form. So it comes from a constant and it decays to a constant, and so basically these are the kind of solution we could also identify. So thank you a lot for the attention. Sorry for the inconvenience in between, and I hope I could show you something about how you can classify these solutions. And currently we are still, this is 1D, and what can we do with it now? Because like usually we want to consider like higher dimensional systems, and therefore we kind of currently working on how we can generalize this or can extend on this. Thank you for your attention, and thanks for having me here.
Thanks, David, and don't be sorry. It's all about the comeback, and I think that went perfectly. Thanks. So questions?
In your original equation was some potential V of x, and then it disappeared somehow.
Oh yeah, exactly. You're absolutely right. So like generally, of course, you have like so initially I think Gross-Pitaevskii just had the self-modulating term added because they didn't consider that trapping was possible, but nowadays it's possible. And for the potential, we kind of have like a box potential, or we have a potential on the ring, and we're working on doing this for other potentials, but this is kind of much more complicated, since if you like use the Madelung transform, there's an integral appearing which has the potential, and then you multiply it with the derivative of the modulus of the wave function times the modulus of the wave function, and over the spatial coordinate. And like for constant potential, you can straight away solve this. This would just give you the modulus squared over 2. But like for other potentials, this integral is kind of not directly applicable and so solvable. So of course, this is kind of what needs to be considered if you want to. So this is a homogeneous case for box or periodic boundary conditions. Yeah.
So you had a term alpha, and if I move back kind of fast, but if alpha was a constant, that's like no current or. So alpha is like setting a boundary condition for the flow of the field or some kind of current.
Yeah.
System.
Yeah.
Is that how I should think of it?
Yeah. So exactly, this is a good way to imagine it. Like as I said, like if the intercept with the y-axis needs to be smaller or at most 0, and if alpha is equal to 0, you have just box boundaries where you have no phase. Basically, like in the stationary case, you have no phase.
By setting alpha non-zero, I can basically think of now I can study problems where there's a flow, some kind of flow or something.
Yeah.
And so would it be possible to add some kind of dissipative terms so that you can figure out what the transport?
Yeah, that's very good that you bring this up. Of course, normally in elastic scattering, free-body scattering is nothing like experimentalist. There is elastic scattering, but usually kind of experimentalists think about three-body collisions in a bad way, because usually they are give rise to recombinations. So for example, two molecules or atoms or three atoms scatter, and two form a shallow dimer, and the third one carries away the binding energy. And this is kind of destroys the Bose-Einstein condensate. And this is usually what happens, what three-body interactions are. And you kind of can model this by giving inserting complex valued interaction strength for the three-body term. And we are currently investigating this, since this is kind of something that could be interesting if you have the analytical solutions for that.
Yeah, if you want to condensate, you want to understand how it gets some little bit of resistance or something.
Yeah, exactly. Yeah, that's something that we're considering currently.
Yeah, and it's a very attractive.
Yeah. Thanks for the remark.
Thanks, Scott. Questions on Zoom?
Yeah, that's.
Yeah, I've got one. Can I ask one?
Just 1 minute. Sorry.
Hi, can you hear me? This is Keith.
Yes.
So sorry, I was kind of like in the middle of two questions. could you please repeat the beginning of your questions?
Yeah, so
I haven't even started yet. Okay, so let me start.
Sorry, on Zoom, could you, here was one additional person in the room who wanted to raise this question, and I would go for that first, and then I come back to you.
Okay.
Since I was not aware that you also had a question, and I kind of looked at him first. Thank you.
Sure.
So for the high order, so for the non-significant high order and don't find something but so why do you choose especially the transformation in that way?
Yeah, go back. Yes, like you mean the Madlung transform? You mean the Möbius transform? When you transform, map the two differential equations onto each other. Okay, that's pretty much the last slide.
So further about the F
yeah, this one. So you might want to know how this comes, and you want to understand how this particular form arises for the gradient transformation. So basically, you can just start by looking at the polynomial in the quadratic polynomial, and then you set in and when you're going from quadratic to cubic, for example, and beginning to transform the roots. So we kind of plug in for n tilde, we plug in this expression here, and then we kind of gather terms, and then we look for, okay, how do we need to choose A, B, C, D so that one root is mapped to infinity. And this is kind of what we do for the density here. And then you kind of can choose it in a way that it's mapped to infinity, but then still you are left with the denominator. So you still have in every four factors here appearing Cn plus T. So this is appearing in every brackets here. And so how do you get rid of this term in the denominator? Well, you need to adjust the gradient accordingly. Then you plug in here the gradient, since this gives rise to 1 over Cn plus T to the power of 4. Then you plug in the gradient transformation, and if you square this, if you insert it here, if you replace the gradients, then you would get the gradient of n squared over Cn plus D squared, which is exactly which we get on the other side, and then you can just cancel it. Then it gets away. So this is why we need to adjust the gradient to, otherwise we would kind of not transform a polynomial to a polynomial. Yeah, still it's still a Möbius transformation for the density, but the gradient of the density. So basically you have distinguish. You can transform the differential equations, and for that you also need to adjust the gradient. But you can also transform the densities, and for the densities you just need the Möbius transform.
So if I may piggyback on that question, so I think it boils down. So what is this? What was the meaning of this total notation? Does it just refer to the two arguments respectively, or what exactly? I mean, this is the Möbius transform, but this I mean, this whole thing is not, right?
Yeah, exactly, Christian. So the density transform according to like a real value Möbius transform with real value coefficient, but the gradient does not. So the gradient is also a fractional transformation, but as you see, it's not even the same transformation when going from quadratic to cubic or go from cubic to quadratic, which is the case kind of for the density. It's still a Möbius transformation in both directions, but for the gradient, this is not the case. And this is you need to kind of pull a root, and if you do so, you kind of need an additional root coming from the other side, so to say, and you need to multiply it, and then you would kind of get this root here when you're going from cubic to quadratic, which is in the denominator here. So like this is kind of the root you get.
Okay.
And of course, you need to be careful. Like AB times minus BC must be unequal to 0, since otherwise the transformation is not proper.
Yeah. So in other words, the generating matrix of the Möbius transform has to be announced.
Yeah, exactly.
Okay. Thanks. So now on Zoom.
Sorry, now I come back to you.
Sure. So I just want to be clear because I missed a little bit of the beginning. You're looking at the Gross-Pitaevskii equation without a trapping potential. So the right-hand side has no forcing term on it. just a homogeneous term. Yeah. So yeah, exactly. So this is if psi is 0, the right hand side is 0. Okay. So, oh no, but you have a v. So the v is prescribed. So the capital V, and what is the form of the capital V?
So basically, I left this open since the solutions as valid for box or periodic boundary, and kind of depends what you impose, which kind of conditions then apply to the roots of the polynomial you get. For example, for box boundaries, you had n1 must be equal to 0. If you just have a a particle in the box scenario for this differential equation, where v of x is just an infinite box.
But it does v have some variation inside the domain? It's not constant, so I don't understand.
No, it's basically just like yeah. So basically, it's given by a step function. So you can think of this that way. So this is kind of what we did. So maybe this is kind of intriguing and not leading you into the right direction. Maybe I should have written it down or pointed it out clearly. But thanks Sue for like.
Okay, and so that then my question is, what do you know about the stability of these structures that you have, these waves?
Yeah, exactly. There's like for the solitons, you for example have an interesting criterion that was derived for a wide class of Schrödinger nonlinear Schrödinger equation, which is the Vahitov-Kolokolov criteria, which basically is a derivative of the particle number with respect to the chemical potential, and then you can distinguish if it's like a stable soliton or if it would decay. The solutions for the 1D Gross-Pitaevskii equation without the three-body term, they are stable, and for the three-body interaction term, the soliton I mentioned with the power law decaying tails, this is unfortunately not stable. So, but the other solitons which you get, like which are just the Möbius transform of the two-body solitons, they are also stable.
Yeah. Okay. So if your potential V does have spatial variation inside the domain, is that physically interesting or?
Sure, that's interesting, but the method is kind of relying on that was the first question, and as I already tried to explain there, it's possible to, of course, you are interested in trapping and going to further dimension, but or like consider this in 2 dimensions or 3 dimensions, but it's like difficult since the system is not, there are few systems for nonlinear differential equation which you can exactly integrate. So this is kind of like the starting point, and we want to see if we can like use the solution perturbatively to kind of go beyond that and like maybe include or consider trapping, but it's not straightforward.
Okay. Well, if V is conoidal or also of this, then you can do it. That's been done.
Yeah, if it's like like a periodic elliptical sign or cosine potential, yeah, that you could do, that you could consider like kind of like an lattice or something like this, where you can like, just like
that has been done. Yeah.
Yeah.
Okay.
Exactly.
Yeah. Okay. Good.
Okay.
Are there any additional questions online from like?
Yes, here. This is Mohsen Zayrnuri from the Department of Mechanical Engineering and Statistics and Probability. I have a question about this various slide. What is the range of length scale that you're going to apply this 1D equation at?
Sorry, could you like?
Yeah, so this, you are studying this one-dimensional equation in the hydrodynamic framework. So my question is, what is the length scale of the problem that you are trying to use this equation to solve your hydrodynamic problem?
So typically, it's kind of, so it depends. If you like have a homogeneous Bose-Einstein condensate, you often consider the van der Waals length. You might recall like this van der Waals potential or the Lennard-Jones potential, which is 1 over r to the power of 12 minus 1 over r to the power of 6, which kind of has a repulsive part to it, and longer range part, attractive part to it. And so the kind of characteristic length scale, which comes down to the homogeneous case, is usually like the van der Waals length.
Mm-hmm. And so in this equation, can you see this as an eigenvalue problem? essentially, because you have a nonlinear operator on the left-hand side and you equal that with mu psi. So can you think about this problem as a nonlinear, time-independent Schrödinger equation with an additional term, and you are interested in finding the eigenfunctions of this operator?
Yeah, exactly. This you can do this, and you can do this, for example, for the two-body case. And if the parameter k, which kind of quantifies the departure from the unit circle, as I said previously, if you perturbatively think about k is going to 0, you would just recover the particle in the box eigenenergies, for example, then with some like correction term, but the zeroth order basically gives you then the particle in the box eigenenergies. So this is kind of exactly like you said, you could consider this like an eigenvalue equation with a nonlinear operator, and can also, of course, calculate the eigenenergies.
I see. It's wonderful. So, and is there any connection between this Gross-Pitaevskii equation and kinetic theory at mesoscale? Is that any possibility that we can a corresponding equation that translates into a subcontinuum, kinetic theory, that you can define the nature of interactions in there as well, and you define, instead of psi, that you can later on find the PDF, you directly solve for the number density. Is that any possibility?
Oh, we haven't considered that yet. So you mean like you can use this like as a starting ground to go to a larger length scales and describe some kind of different physical system with this kind of method? Or
Yeah. It's basically what you have right here is just simply the balance of the energy, kinetic, and potential energy plus the interactions. That's kind of a new version of the Schrödinger equation you have in a time-independent framework. But you can define this very problem at a kind of a mesoscale that is connected to your hydrodynamic range of the scale as well.
I see.
And you can define the two-body, three-body, all types of simple to more complicated interactions at the mesoscale as well. So I wonder if there is any corresponding to this GP equation, but translated into the kinetic theory of Boltzmann. So
I can look into this. This would be very neat and interesting to look for this. I'm not aware of this. The Gross-Pitaevskii equation, or the nonlinear Schrödinger equation, as I said, is used in really a lot of a bright range of physics. And as I'm coming from the point of cold atoms, I consider this to call it the Gross-Pitaevskii equation. But of course, it's just a nonlinear Schrödinger equation. And maybe there is, I cannot definitely give you an answer to that, but thanks for the suggestions. I will look into this, and maybe I can email you if I find something. So maybe you can write down your email in the chat, and if I do some research on that, I can email you if there's something that that would answer your question. Or I email you anyways, even if I find nothing.
I really appreciate that. Thank you very much.
Thank you.
Any questions? Okay, then let's thank David again. The talk was the good news, not the bad news. This is very likely the last seminar in the series, at least for this season. Thanks for joining in, and thanks for attending, and thanks to Elizabeth for the refreshments. Yeah. See you around. Bye.
Okay. Thank you.
All right. As well.
Could you understand me, or was it talking too fast, or was this?
I won't lie to you, it was quite fast, but I think it was one could comprehend.
Okay.
And so in a way, so that I think that we had to stop for, I don't know, a minute or so. That helped to, settle down things. And so it was just
I was a bit of nervous, and then I start to speak much more rapidly, and so sometimes I maybe need to practice on that to kind of keep more calm and keep my speaking speed down a bit, so that I don't
I mean, it's all about practice, right?
Yeah,
So
yeah, exactly.
if you don't mind, 2 quick questions.
Yeah.
The first one is a subtlety, and the second one is hopefully not very technical. So what about the time dependence? I mean, you have t as the argument, but this is, I mean, time independent
Yeah, sure.
equation. So can you go to time dependent?
Yeah, sure. Like if you have like the eigenenergies, for example, we want to like see what happens if we have this dissipative term and what happens to the eigenenergy then in the 3-body case. So how are gonna they behave, and do you see kind of a leakage or what's gonna happen there? So of course we want to consider this.
And so how would the just very briefly, so how would the analysis change, or would it change a lot when this is a time dependent process?
So like for a time dependent process, I think it might be quite complicated to integrate this into the framework of the algebraic curve we use.
He's basically looking for steady state solutions, right? The ones that just get multiplied by a phase. And so for the general initial conditions, it's going to be some complicated mess.
Right. So this
Modelung.
So I mean, that's exactly what Dean just said, right? So you factorize the density or the square of the density, and then you have just the phase, right?
Exactly.
Okay. And then the second question is your very last slide. In your very last slide, so you have this.
Maybe you just go to the.
So this is not a technical question. I'm just interested in the conclusion. Yeah. Here, perhaps the next one. The previous one then. So okay, so this conformal duality.
Yeah.
I think I got the gist of it, and that's essentially what's in the next slide. But what is sort of the takeaway message of that? What can I do with that? How can I use it? How can I take advantage of it?
So
and what for?
Yeah. So kind of this is like some mathematical trick which has been used for elliptical curves previously. So we kind of rediscovered this in a physical context. So kind of this transformation for elliptical curves has been around there for a long time. And you can even do this for like hyperelliptical curves. So if you even have like, so as long as you have like an even leading power, you can always bring it down by 1 degree. So this is even possible if you would include 4 and 5 body
Is it really
interactions.
always, or is it sometimes where this singular transformation just bombs? I mean,
Yeah, exactly.
You would think if I add a cubic term, if it has a certain sign, I mean, the whole character of this physics could change. It could be unstable or something.
Yeah, so the character of the solution, of course, it depends on the coefficients you choose to transform it. You can kind of